Hello everyone. In this video, I'm gonna talk about hydraulic components of a warping machine. So, what is warping machine? Warping machines are essential equipment in the textile industry used in the process of warping, which involves preparing yarns for weaving by winding them onto a warp beam. So we can say that the major components of warping machine are creel and headstock. And you see here the creels. The creel is a structure for holding supply package, and the headstock is included by it includes winding and machine control unit, and this winding itself includes the beam or the drum section and the hydromotor for driving this beam and and the drum. So here I'm gonna show you a short video about this warping machine. You can see here this is the beam or the beam, and this is the hydromotor. This is an axial, I can say radial piston motor, and this is the control unit. And here is the creel section. You can see here, yeah, the creel section and the hydromotor, the control section, and the beam. So here, yes, the warping machine hydraulic circuits is like as this. You can see here that the here this section, you can see here that the warping machine has this hydraulic circuit. This hydraulic circuit is composed of two sections. The first circuit for the hydromotor, as you saw in the video, this hydromotor has to be driven by a hydraulic pump and electromotor. And the second one, this is for the positioning or positioning of this we can say that this drum or beam. So even this one, this is an arm, a hydraulic arm or hydraulic cylinder, which is used for lifting and positioning the warp drum and adjusting the tension and loading and unloading this beam. So in this video, I will not talk about this section. In the second part, I will talk about this section. But however, in this first section, I will talk about this hydromotor circuit. As you see here, this is the tank, and this is the electromotor. Electromotor is used for driving the pump, and the pump here. Let me do this one. Okay, so the pump here, you can see here that the pump here obtains the oil from the tank and pumps the oil throughout this block. What is inside this block? Inside in this block we have a directional control valve, a four-way, three position, one, two, three position directional control valve that is operated by solenoid. And this here, you can see here, these are the symbol of using solenoid, and this is the symbol of the spring. It means that it is operated by a spring and the solenoid. And what are these? And these are the counterbalance valve, or these are used for braking this hydromotor after it's been stopped. So I will explain in the next section why we are using and these counterbalance valves and how they are operated. So all of these counterbalance valves and directional control valve and the pressure meter are located, and all of these ports are located inside a block. And let me explain the counterbalance here. What is this counterbalance? Okay, so as we know, when we keep the lever of this four-way three-position directional control valve in the middle position here, the motor will stop. Obviously, the motor will be stopped because all of these ports are connected to each other, and there is no any pressure here. Even if there is a pressure with by the pump, it will go again. The pressurized oil will go back to the tank. So in this section in here, whenever the directional control valve is in the position, we have two main issues. The second is that motor may overrun due to overrunning load, and the load may fall because this hydro motor is connected to a shaft and to the drum or the beam, and so obviously the drum and the shaft, all of them are very heavy, and they can be fall, or because of the inertia, motor continues to rotate for considerable amount of time before it comes to rest. It means that whenever we we change the in the first section, for example, whenever the motor is running in reverse or in forward direction, and we stop the motor, and so the motor, because of its own inertia, will continue to rotate, and that is a problematic issue. So in order to avoid this issue, we utilized brake valves B1 here and B2 to in order to solve this problem. In the first position here of this, I mean in the left position, whenever we change the position, this position comes here, and so the A is connected to B. It means that pressurized oil is connected to A port, and the and the to pressures all to A, and B to the tank. You can see here B is connected to the tank. If we just connect, we just change this position to here. So accordingly, the motor will run in forward direction. You can see here, whenever pressurized oil goes to the A port, it comes here from here, and it will make the hydromotor to rotate in forward direction. However, in the second position, or in the left position, whenever we change the position of this directional control valve by the lever, this one will come here. So what will happen? In this scenario, we will have pressurized oil to go to the B port, and a comeback oil, or on the oil that doesn't have any pressure, will come back to the tank from the outlet of this this motor. So in here, whenever pressurized oil is going to B port, it will make the motor to rotate in reverse direction, in this direction, like as this. So the outlet of the pump, the motor will goes to the tank here. So in the middle position of four way three position directional control valve, all ports are connected to each other. Here you can see all ports are connected to each other. If the motor is loaded with overrunning load, and if brake valves are not used, then the load will obviously fall. In the circuit shown in figure, there are two brake valves, B1 and B2. These brake valves will allow oil to flow out from the motor if and only if there is pressure at the inlet of motor here. So if oil is not applied to inlet of motor here, then its outlet will not open, and the motor shaft is locked. Look at here. This is very important here. If these ports are connected to each other, that means that there is no any pressurized oil, because the pressurized oil will come back to the tank. So if there is no pressurized oil here, this pilot operated this valve is operated by pilot, the hydraulic pilot operated valve. So there is no any pressure here to make this one to be open. And this check valve, it's already closed. So whenever the motor is stopped, this oil will not have any way to go out, and that means that the oil will be trapped here. And again, even here, and this valve, uh, whenever sends this pressurized pilot or pilot operated valve, since there is no any pressure here, this pilot will not make this pilot oil will not make this valve to be open. And again here, this valve here is already, this check valve here is already closed, so the oil will be trapped here. And so the motor itself and its shaft will not have any space to rotate, and it will locked in its place after being stopped, after we change this directional control valve in the middle position. So in the next section, we want to say how we can select this hydromotor and the pump and the electrical motor to make this circuit to work. I mean, we have to calculate all of these requirements for this specific warping machine hydraulic system. So here, I mean, we want to design a hydraulic system for a warping machine. For this, firstly, we have to select the desired hydraulic pump and motor for the driving beam. To achieve the highest performance, we need approximately 1,700 Newton meter to torque to be delivered by the hydromotor at 120 bar pressure and 120 RPM, which means 2 revolution per second motor speed. Based on the desired power and price, we can select the R8M1000 hydromotor, which has 992 cc or cubic centimeter, which is equal to 992 multiplied by 10 to the power of -6 cubic meter. Maximum speed of this motor is 330 RPM and maximum pressure is 270 bar and 56 kilowatt according its data sheet. This is the technical data sheet of this motor, this sheet. You can see here this R8M1000 has displacement of 992 cc and theoretical torque is 15.8, maximum constant pressure is 270 and maximum continuous speed is 330 and maximum continuous power is 56 and its weight is 92 kilogram. And so this is the catalog of this radial, this single displacement crankshaft radial piston motor. These motors are applied in marine equipment, winches, conveyors, injection molding machines, steel bending machines, dumpers, agricultural and forestry machines, airport machinery, etc. So you can use this, and it has such product features high volumetric and mechanical efficiency, very smooth running at low speeds, high starting torque, constant torque, wide speed range, and etc. And all of these, a series of these motor have been provided here with their technical data. So we just selected this one. Thus, accordingly, we have actual flow rate. How we can calculate the actual flow rate? The calculation of actual flow rate is very easy. It is equal motor speed multiplied by volumetric displacement, which is equal to 9 multiplied by Vt, or volumetric displacement. So we already know that the motor speed is 2 revolution per second, which is equal to 120 RPM, multiplied by 990, multiplied by 10 to the power of minus 6 cubic meter per revolution, which is equal to 1980 multiplied by 10 to the power of minus 6 cubic meter per second. So here we just converted cc to cubic meter to cubic meter. So hydraulic power delivered to motor here is equal to actual flow rate multiplied by system pressure, which is equal to 1000. We already calculated the actual flow rate, which is equal 1980 multiplied by 10 to the power of minus 6 cubic meter per second multiplied by 12 multiplied by 10 to the power of 6 Newton per square meter. What is this? This is the 120 pressure bar, 100 pressure bar, and we have converted 120 pressure bar to Newton meter square. So the hydraulic power delivered to motor is equal to 23.76 kilowatt. It means that we need this power to be delivered to the motor. This power is delivered to the motor by what? Obviously, it is delivered by the pump. You see here, this pump has to deliver 23.76 kilowatt to the motor. So volumetric and mechanical efficiency of motor are 97 and 92% respectively. Therefore, we have power delivered by hydromotor is equal. So we get this 23.76 power from the pump. It's delivered to the motor, and the motor itself will deliver power for us, obviously. So this power can be calculated by its efficiency, efficiency of volumetric efficiency and mechanical efficiency, which is equal to 23.76 multiplied by 0.97 multiplied by 0.92 mechanical efficiency, which is equal to 21.2 kilowatt. That is equal to 21,200 Newton meter per second, because we converted kilowatt to Newton meter per second. So torque delivered by motor is equal to power delivered by motor divided by motor speed. Accordingly, we have 20 here. The power delivered by motor is equal to 21,200 Newton meter per second divided 120 multiplied by 2 pi divided by 60 second. I have forgotten to put a second here, so this is 60 second, because we convert 120 RPM to meter per second, obviously here. So we can here do revolution per second, not meter per second, because we already have meter here. We have to just change this minute, because RPM means revolution per minute, and we convert that RPM to second. So here the second goes with this second, and so we will finally we will have Newton meter for torque, which is equal 1700 Newton meter. Since the motor actual flow rate, this is very important here. This one is very extremely important. We have the motor actual flow rate is equal the pump actual flow rate. Again, we have motor actual flow rate is equal to the pump actual flow rate. So accordingly, we have pump actual flow rate is hydromotor flow rate divided by hydromotor volumetric efficiency. So it is equal 1980 multiplied by 10 to the power of minus 6 cubic meter per second divided by 0.97 volumetric efficiency of this hydromotor, or our radial piston hydromotor, which is finally we have 1920 multiplied by 10 to the power of minus 6 cubic meter per second, which is equal 115 lpm or liter per minute. Then we have to choose. So that what does it mean? This means that we need a pump to deliver this flow rate for us. We have to select a pump which can deliver this kind of LPM, this flow rate for this flow rate for us. I mean that we have to choose an electromotor and a pump in such a way that we can address the required flow rate of this 115 lpm, which is equal to 1920 multiplied by 10 to the power of minus 6 cubic meter per second. So if we select a Rexroth with 95 cc of volumetric displacement and electromotor with a speed of 1500 rpm and power of 30 kilowatt, we can achieve the designer system's requirement. Look at here. This is the data sheet of this, the technical data of this A11VO series of Bosch Rexroth pumps. So here the size is 95 and maximum speed is 2350. All of other power 128. Torque for all of them are provided here. And this is the catalog itself. So you can see that nominal pressure is 350 bar and maximum pressure is 400 bar. That is used in open circuits. So the variable axial piston pump of swash plate designed for hydrostatic drives in open circuit hydraulic system. These are the features. You can download that and review the technical data of these pumps, these series of pumps. You can see here all of these data have been provided here, and I have taken my pictures here, my pictures from this one, from this page. So here we have to examine why our selection is correct. If I'm telling that I have to select this one, why this idea is correct? So we have to calculate to see if this one satisfies our requirement or not. We have pump theoretical flow rate is equal pump volumetric displacement multiplied by pump speed. Here one pump volumetric displacement, theoretical displacement is 93.5, but obviously at speed of 2350, but we will not achieve this one. This is the maximum one. We need we can have this 80 cc, which is reasonable for our requirement. because, as I said, because we will not achieve this maximum all the time. If we have 80 multiplied to the 10 to the power of minus 6 cubic meter per revolution and multiplied by 1500 revolution per second, we can calculate our pump's theoretical flow rate. So here why I selected this pump speed 1500. As I said, we have to because of this because of the electromotor. Whenever the electromotor has 1500 rpm, that means that because this shaft of this pump is coupled with the shaft of this electromotor, the pump will have the same speed of 1500. Look at here. You can see that the shaft of this pump, this pump and the electromotor are connected to each other, coupled to each other. It means that they will have the same revolution. So if we select this pump speed as 1500 revolution per second, and this pump volumetric displacement of 80 multiplied by 10 to the power of minus 6 cubic meter per revolution, we will have 2000 multiplied by 10 to the power of minus 6 cubic meter per second, which is equal to 120 lpm. Accordingly, we have calculate the pump actual flow rate. That one was theoretical flow rate. Pump actual flow rate is calculated by pump theoretical flow rate multiplied by pump volumetric efficiency, which is 0.97. 2000. So we already calculated the theoretical flow rate, which is 2000 multiplied 10 to the power of minus 6 cubic meter per second multiplied by 0.97. Finally, it is equal 1960. I think here it's not correct here. It should be 1940 because I already have calculated this one. Let me calculate it again. Maybe I'm wrong. So here we can say that 1000. Yes, here we can say that 2000 here multiplied by 0.97 is equal to what? Oh, yeah, 1994. So I can say that this is not correct. So I can use that. I can select this one, and so yeah, here I can select this one, and for here I have to select this for here. Okay. Yes, this one 1940 multiplied by 10 to the power of minus 6 cubic meter per second, which is equal 116 lpm. This one is very close to 115 lpm. We needed, as I said here, we needed this 115 lpm pump to deliver lpm flow rate, that pump to deliver for us for the hydromotor. So we can say that since we we can say that our selection was very correct, almost correct, because it is just 1 lpm more than our requirement. But if it is 1 lpm is more than 115 15 LPM, it's very good. It is satisfying our requirement. So finally we have actual power delivered to the pump, which is equal electromotor power multiplied by efficiency. Here electromotor power, as I said in the previous page, is equal 30 kilowatt multiplied by its efficiency is equal to 0.95, which is equal to 28.5 kilowatt. So hydraulic power delivered by pump to the hydromotor is equal power delivered to the pump multiplied by efficiency, which this actual we have the actual power delivered to the pump, and again multiplied by the pump efficiency, which is equal to 28.5 kilowatt multiplied by 0.93, which is finally is equal to 26.5. So hydraulic power delivered to the hydromotor should be 2670.76 here. We need this power to be delivered to the pump, 26.76. So here we achieved the hydraulic power delivered by pump is 26.5, which is very close to, it is even much, a little more than, not much, a little more than 26.76, which means that it is very satisfying to our requirement. Finally, we can say that our selection, the selection of pump and electromotor, satisfy the design requirements. So far I have explained the machine, the definition of warping machine, its component, and I showed you the video of radial piston motor and and its application in the warping machine system, and I explained its circuit, hydraulic system circuit, and I explained it counterbalance, and explained the calculation and requirements of the system. Finally, I'm going to show you the simulation of the system, controlling system by the Automation Studio software. I'm not going to explain the entire Automation Studio software because you may already have information about the software, or if you don't have, I will prepare another video explaining this Automation Studio software of designing hydraulic systems and even the PLCs, which is used for controlling this hydraulic system. And this is a very handy, very useful software. So I already have designed this. This is very simple design of just it is for education, because in reality is much more complex than this one. You can see here that this is the actual and here you can see that this is the hydraulic circuit, and this is the we can say that this is the PLC. So I'm going to run this system for you. So you can see here that this is the hydraulic pump, directional control valve, 3-position directional control valve, which is operated by solenoid and controlled by the PLC, and these are counterbalance valves and the hydromotor. So, and this is the HMI human machine interface. So if we start forward, you can see here that what happened here. When we click this start forward, this input start forward was here, this as an input, and it made this the ladder program to be activated, and the output to be activated accordingly. Whenever the output B is activated, it means that the output B is connected to this output of the input of this directional control valve, and it will make the directional control valve to be open here. The pressurized hydraulic oil connected to this port, and this port will make the hydromotor to rotate in this forward direction. And so whenever we stop, you can see here that N2 input of the PLC is green here. It means that it is activated. When it is activated, it means that the pump is stopped and the hydromotor is stopped. Why hydromotor is stopped? Because of using these brake systems, brake valves. So in the reverse direction, whenever we click this button, you see that NIN input 0 here in the PLC section, input 0 is activated, and whenever it is activated based on the program of the PLC, the output 0 is activated. The output 0 is connected to the A section of this directional control valve, means that the solenoid will change the position of the directional control valve to the left section here. Then accordingly we will have pressurized oil to come here and go to the inlet of this hydromotor, and will make the hydromotor to rotate in reverse direction. So that's it. If you have any question about the calculations and simulations of the system, you can directly uh, 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 ask your question in the comment section. See you in the next video. Thank you so much.